So off we go. One of the questions was, is climate change permanent? Is this something that we're going to be stuck with forever? And the answer is no, it's not permanent. What's going on in the atmosphere right now by putting in additional greenhouse gases into the atmosphere, you've probably heard about it. We're, as a society, global society, getting most of our energy from burning fossil fuels. You burn carbon, carbon-based fuels, whether that's natural gas, whether that's oil, whether that's coal. You burn them in oxygen, because we do have a lot of oxygen in the atmosphere, and that releases heat energy and carbon dioxide. And now that we got 7 billion people running around the planet, it adds up. So it takes a little while for the atmosphere to respond to the additional carbon dioxide. It doesn't just like, oh, the next day it's going to be hotter. It takes a while for the entire Earth system to respond to this kind of forcing. Plus, we're still forcing it. It's not like, there was 350 parts per million of CO2, and then suddenly there was 400. So now let's wait until the atmosphere comes back into balance with this new forcing. It's like my oven was cold, and I just turned it up to high, and it's not instantaneously hot. It takes a while for the oven to heat up. And it's a very similar situation with what we're doing in the atmosphere, right? Now, the reverse is true. If we can find a way to artificially remove carbon dioxide from the atmosphere will also respond. It will probably take a few decades, but it will also respond. And in some of the videos and lectures we'll have later on through the semester, you'll see the kinds of timescales that works on. It's slow compared to a human lifespan, but geologically it's pretty rapid, at least what we're doing as humans. Another question I got, which I love, is that all about climate models, and somebody said, well, the climate models aren't as good as they used to be, which is just, sorry, that's just wrong. I mean, the climate models are getting better all the time. Having said that, it is a tool. Climate models are tools. They go back to that mathematical representation of the climate system, a mathematical model. It's a representation of the climate system. Trying to mathematically represent everything that we understand scientifically about the relationships in the climate system. And because we don't know everything about everything all the time, we have to make some guesses, and some guesses are better than others. So you use the climate models as a tool to say, okay, what kinds of things are possible? What kind of things should we be on the lookout for? Knowing what we know now, where should we put more of our resources in terms of adaptation, mitigation, trying to shore up infrastructure? Where is our time? Where are our resources best spent? All right. I'm with a lot of folks who are concerned that there's too much credence put into the climate models. They are very important tools. They do give us a window into the future, but it is not a crystal clear window into the future. All right. It's kind of like having a window, but there are a few cracks in the window, and I can kind of make this out, but that part looks a little fuzzy. I could look down there, and that one makes a lot of sense, but that over there looks a little bit fuzzy. So that's the situation with the climate models, but they do get better, because as computing power gets stronger and faster, we could take the knowledge that we have learned as a scientific community about the Earth system, all right, and then run more complex climate models and see what happens. All right, so I'm absolutely on board with the idea that you don't just blindly trust a model. You don't blindly trust a weather model either, for that matter. All right, but it's an important tool. And like any tool, you can use it correctly or you can use it incorrectly. But you don't throw your tools out because this tool, this hammer isn't really good at opening a window, so I'm not going to use this hammer for anything. No, you use the tools wisely. So that's my little spiel on climate models. What can we do to combat climate change? Well, there's two ways to do this. There is bottom up and there's top down. Now, there's no one thing that you or me can do to fix the whole thing by ourselves, because no one person caused this thing. All right. What you can do as an individual is monitor how you are using energy. You hear things about your carbon footprint. All right. And there are lots of these online tools for carbon footprints and the like, and they're all good. So see what you do in your day-to-day life that you can change. Do you walk more? Do you combine trips? Do you drive less? Do you set your heat back a degree or two in the winter, up a degree or two in the summer? Do you find yourself throwing away a bunch of stuff? You could consume less. I mean, this is a consumer society, but use stuff you have, recycle things that you don't need anymore when you can. Those are the things that we can do as individuals. And most of the time I hear, well, I can't afford an electric car. I'm like, well, you don't need to have an electric car. You can aspire to that. Great. I mean, I don't have an electric car. I want one, but that's just not in the budget right now. That's just the way of the world. But you could do other little things, cut back on waste, because it takes energy to produce stuff, whether that's food, whether that's clothing, whether that's building materials. All right. And again, we don't all have to go live in caves and never buy anything anymore, but be a little more mindful of how you are spending your individual capital, your individual energy. And there are a lot of these carbon footprint things out there. So don't just take one of them as being this the end all be all. Look at 2 or 3 of them, all right, and see, okay, this kind of makes sense. This kind of makes sense. This kind of makes sense. I mean, a big one is flying, air travel. That's huge. That's huge. And there's been a lot less of that lately, obviously, with the pandemic and stuff. Now, I like a good trip as much as anybody else, but I haven't gotten on an airplane since 13 months ago. All right. And I don't fly a lot in the first place. But anyway, you look at those things and see what you can do in your own life to change your behavior a little bit. The timelines of climate change, when we talk about what's going on right now, I think it's really the last 10 to 20 years that we are seeing the climate change signal emerge from the noise, if you will. Again, we talked about this last week, and in the lecture notes this week, or lecture video, there's all this up and down within the system. All right, the Earth is always going through these little ups and downs in what we think of as our normal climate, the climate of the last 100, 200 years. There are warm years and cold years. But over the last 20 or 30 years, there really haven't been any cold years. I mean, the cold years are like we think about globally, not in an individual location on the globe, but globally, they're just not happening anymore. They're just not. I mean, yes, it's still cold in the Arctic, and it's still very cold in the Antarctic. But what we need to do is kind of retrain ourselves to think about what's cold and what's not. For you and me, 15 degrees is cold, no question. But it used to be more regularly, let's say 5 degrees or 0 degrees. All right, so it's still cold, but we don't get the extent or the length of time or the severity of cold as frequently as 50 or 60 years ago. So when we think about the time scale of, that's what we've already seen happen. How much more warming takes place depends a lot on what we do in terms of putting carbon in the atmosphere in these next 20 to 30 years, because the level of carbon dioxide in the atmosphere is now up past 410 parts per million. And that's up 35, almost 40% since the mid 1950s. So it's a big jump, and there's no way you can attribute it to anything else other than humans burning stuff to generate energy. So if we start to curb that quickly in the next 10 to 20 years, we will probably see the average temperature of the whole planet up 4, maybe 5 degrees Fahrenheit, and then level off in the course of, let's say, 70 to 80 years. And these are ballparks, just to give you an idea of a sense of scale, whether it's 69, 81 years, whatever, but just to wrap your head around a sense of scale. It's not 600 or 700 years, but it's not 1 or 2 years. If any of you guys saw the movie The Day After Tomorrow, which was just hysterical, I worry that when we'd say as a scientific community, things are happening rapidly, to the general public, they envision rapidly as 3 days. And the climate isn't going to change in 3 days. And this is a communications issue with the scientific community. We need to continuously convey, because I fuss at them. I fuss a lot of people for saying how, oh, climate's changing so rapidly. I'm like, not to my sister. She doesn't know any better. You have to remind people about the time scales of climate. So when we talk about climate change and time scales, that's what we're referring to. If it's so damn bad, why aren't we doing more about it? Well, that's a really fun question. There are a lot of competing interests, especially in a capitalistic society. And I'm not going to start riffing about economic theory here. But the reality of the situation is there is money involved. I mean, there is money involved one way or the other. There is resistance to change. So there are elements in any society that are just resistant to change. And the other thing I will say this sociologically is that it's not immediately obvious that the climate is changing. So again, it's not like you go out in 3 days and went, oh crap, the climate has changed. It takes a long time. It takes a full-on human lifespan to really notice a big difference. And if you're running a company and you're trying to turn a profit in 5 or 10 years, you're just not worried about that. So I think that's a lot of what we're seeing. But we'll talk more about that in policies and stuff later on. How does weather impact the climate of a local area? Let's take a couple of examples for that. So let's say a place like Miami. Well, I think most people know that Miami's warm and it's humid, and it rains a lot. It's warm and humid, it rains a lot, and they don't get below freezing. So we start to see ecosystems in that part of the planet that match that type of recurring weather, a recurring weather pattern, which ultimately becomes climate. It's a climate that never gets below freezing, or exceedingly rarely gets below freezing. So you can count on that. You can count on a lot of rain every summer. You can count on that. That's a climate feature. That's dependable. All right. So those are the things that lead to ultimately, and given the South Florida's height above sea level, or proximity to the ocean and the Gulf of Mexico, that's going to lead to things like swamps and Everglades. Okay. As opposed to someplace like Minneapolis, Minnesota, which is in the middle of the North American continent, and it's pretty flat, and there's nothing between them and the North Pole other than Canada. They are more susceptible to widespread temperature swings. What we'll talk about later in the course is that an area that is close to a large body of water will tend to have smaller fluctuations in temperature through the course of the year. Water is a moderating influence in climate, whether that's Norfolk, whether that's Miami, whether that's San Francisco, whether that's Seattle. Those places close to a coastline, close to a lot of water, tend to have smaller fluctuations in their temperature through the course of a year. They still have seasons, but they're not as pronounced as someplace like Minneapolis, which can get to 40 or 50, well, not really 50, but 20 or 30 below zero in a very cold situation, but still get up to 100 or 105 in a hot situation. And you don't see anything like that where we live in the middle Atlantic, where it's whether me in Philly or you in Lynchburg, it rarely gets below 0 or 5 below, and it doesn't really get much above 95 or 100 on occasion, because we are a little closer to the coast, right? So these are some of the things that go into determining why the climate of a certain location is the way it is. And of course, latitude, north, south, and all that, and elevation, mountains, coast, those are all relevant as well. Right. So we'll get more into the weeds of that a little bit later on. Well, one more thing on that, actually. We talk about the tropics versus the middle latitudes. Why is the climate in the tropics so different than, let's say, in a Virginia or West Virginia, North Carolina, Pennsylvania, New York? Because the tropics get so much energy from the sun all year long, it doesn't get cold. Or it doesn't, certainly not kind of the cold that we get here. So their weather patterns depend more on the contrast of temperatures between land masses and oceans. And we say that because land heats up and cools off a lot more easily, a lot more quickly than water does. All right, it takes a lot more energy to raise the temperature of water than it does to raise the temperature of dry land. And the reverse is true. It takes a lot more, and you have to remove a lot more energy for water to cool compared to allowing land to cool. All right, and one way we see that, if we think about temperatures at the beach or ocean temperatures right along the beach during the spring and summer. If you go to the beach in Memorial Day, early June, the water's still kind of cool. But even if you go to the beach in September or October, even though the air is cooler, the water's still relatively warm. It takes a lot more time, a lot more energy to heat up and then ultimately cool down water. So there's kind of a lag compared to land. So that's one key reason between the tropics and the middle latitudes. And there are other wind patterns that have developed. We'll talk about it. They're called Hadley cells, Ferrel cells, but we'll get more into that a little bit later on into the course. Severe weather. Severe weather, of course, that's why I got interested in weather as a little kid. When we talk about severe weather, for one thing, severe itself is a funny word, because people who do weather forecasting, who are deep in weather science, meteorology, all that stuff, severe means something very distinct. They're talking about severe local storms like tornadoes, small scale windstorms, thunderstorms that are causing damage. So those smaller, and when I say small, I mean something that's 5 miles across, 10 miles across, 15 miles across. That's pretty small compared to the storm that started going through here on Sunday, and it's just finishing up tonight. That's huge. That's several hundred miles across. All right. So any kind of impact on climate change on a very tiny thing, I say tiny compared to the scale of the whole Earth, like a thunderstorm, is very small. You can't say like, well, you know what? My thunderstorm today was worse because of climate change. You just can't do that. Now, we can say other things statistically, like because we know the average temperature is warmer than it was 20 or 30 years ago, that probably provides a little more energy for thunderstorms. So you can make an argument they may be a little bit stronger, but you can't say, oh, this one thunderstorm went over my house, it dumped 2 inches of rain. You can't do that. You just can't do that. So the impact of climate change on individual tiny storms is tenuous at best. That kind of dovetails in this next question about the upper atmosphere and how that affects the weather down here. And by that, we have to be careful about what we say the upper atmosphere, because most of the mass of the atmosphere is in the troposphere. We talked a little bit about this in the videos, the levels of the atmosphere. Troposphere is the lowest one where we live. That's where all the weather's happening. The next one up is the stratosphere, and that's where you start to see, that's where the ozone layer is. So that's where solar energy, the ultraviolet spectrum part of the solar energy spectrum comes in and is absorbed. Most of the UV, not all of it, but most of the UV is absorbed there. And then you go farther, you get to thermosphere, mesosphere, exosphere. That stuff up there, you're going up miles, okay, that part of the atmosphere. The core of the atmosphere where you could breathe is basically the bottom 10 miles. So stuff that's up 200 miles doesn't play much of a role in our weather at all. A lot of times when you hear a weather person talk about the upper atmosphere or upper level winds or things like that, they're talking about things that are 15, 20 to 25,000 feet up. So 3, 4, 5 miles, certainly not 100 or 200 miles up. There's just a few molecules running around up, 100, 150, 200 miles up. All right. So when we talk about the upper level winds, the upper atmosphere from a meteorology or a weather forecasting standpoint, that is more along the lines 3, 4, 5 miles up. And we'll get more into this later in the course, but the short version is, as those winds move very rapidly or slow down, that induces, if you will, upward motions and downward motions in the atmosphere that we sense down here at the ground in terms of sensible weather. And again, we'll talk about this a little bit more, but the short version is very fast moving air aloft, 3, 4, 5 miles up, is what helps to induce upward motions in the atmosphere between the ground and that level 3, 4, 5 miles up, where the weather's really getting going, right? So inducing those upward motions means air cools, forms clouds, and ultimately rainfall. The very first order. Clearly, it's more complicated than just that, but to the first order, the first approximation, that's kind of what's going on. The reverse is also true, that when the air is slowing down 3, 4, 5 miles up in the atmosphere, it's kind of a piling up of mass, if you will, because things are slowing down, that induces sinking motion. And as the air sinks, it warms, so clouds tend to collapse. And it's dry and it's nice outside. So that's the very wide view of thinking about how the upper atmosphere, 3, 4, 5 miles up, affects the weather down here at the ground. Paleoclimates. How do we know what the hell happened 20,000, 40,000, 600,000 years ago? That's all about paleoclimatology. We'll do a whole lecture on that. And I just reviewed another excellent video from a paleoclimatologist that was on Nova, and I've put that in the Moodle notes. It's called Polar Extremes, and that tells you a lot about how the scientific community has learned about what climates did in the past, and that's a geology thing altogether. I mean, that's why we have geologists. It's not just this rock is a volcanic rock, the end. There's a lot more going on to geology than just that. We could tell a lot about what kind of weather patterns, what kind of climates existed in these ancient time periods, hundreds of thousands to millions of years ago. So that video is up there, and we'll do a whole lecture on that a little bit later on. But, ice cores, sediment cores, I'm more into ice cores and sediment cores, just being a weather dude. But all that stuff is really fascinating. But you need to understand chemistry for that stuff too. You need to understand isotopes of carbon. You need to understand isotopes of oxygen. You need to understand how radioactivity, how things decay. You need to know all that kind of stuff before you start say, well, we know this is what happened with the climate a million years ago. You've got to know what are nature's clues to dating things that go back a long, long way. Natural disasters. Natural disasters have always been there, and they're always going to be there. And this is the other thing. I've heard some people start to call these things climate disasters, which I'm frankly not a big fan of. Um, I like to call these environmental disasters now. It's kind of a catch-all because volcanoes are a natural disaster, but that's not really climate. That's a geophysical thing. There's some people who will swear up and down, well, I can tell that is there a relationship between earthquakes and heat? I'm like, not really. I mean, I'm not going to say put my foot down and go no, but there's no evidence of it. There's no physical evidence of a connection between the weather and volcanoes. In other words, weather causing a volcanic eruption or weather causing an earthquake. There's no physical evidence of that. Now, the corollary to that is, can a volcanic eruption affect the weather? Hell yes. Back in 1991, Mount Pinatubo in the Philippines erupted and put I don't know the number offhand, but it put all kinds of ash and soot into the atmosphere. All right. And it takes about 12 or 18 months for that stuff to settle back out of the atmosphere, because it does go all the way up into the stratosphere. All right. It goes beyond the troposphere all the way into the stratosphere. So it is reflecting some more incoming solar back out into space. So there is a net cooling. It doesn't turn us all into a big icebox, but it does induce a little bit of a net cooling. And there was a very short term, I'd say short term, a year, 18 months, where the planet was about a degree cooler until all that stuff settled back out. And I distinctly remember that summer not being hot. I mean, it wasn't cold. We didn't have crop failures or anything like that, but it was not a particularly hot summer at all, the summer after Pinatubo. So when I think about natural disasters, environmental disasters that are tied into atmospheric things, weather disasters, if you will, by adding energy to the climate system, greenhouse gases adding heat to the climate system. Heat is energy. So we're adding energy to the system. That means more energy is going to be available for these extreme events. The extreme events have always happened. All right. The floods have always happened. The droughts have always happened. The hurricanes have always happened. These things have always happened. They're always going to happen. What attribution science is telling us, or the effort anyway, to figure out how much climate change impacted a particular event is still something that's only been tried the last 15 or 20 years. It's just, and I hate to get but so preachy about all this, but you can never say that this event was caused by climate change. Did climate change cause this hurricane? Did climate change cause this flood? No, but it does play a role. One of my favorite analogies to this, and I'm starting to date myself with this, but in the 90s was a very popular era of steroid use in Major League Baseball. And the analogy here is this. If a dude hits a home run in a baseball game, you can't say that, well, you know what? He's on steroids. He hit that home run, right? But what you can say, when you look at the entire league, there were more home runs hit because there were more guys on steroids, right? So that means the likelihood of home runs or the frequency of home runs went up. It's the same thing when we look at the climate system and how that impacts natural disasters. Sometimes you hear that called extreme weather. Sometimes you hear these called high impact events. I like the term high impact events because I think personally, the word extreme has been tossed around too much. So a high impact weather event. These type of events, things that, they used to happen once every 20 or 30 years. Now maybe it happens once every 10 or 15 years. Or that big storm that put down 10 inches of rain now puts down 11 inches of rain. All right, that flood that used to only go up to here or here, now it's coming up to here or here. So one of my favorite communicators about climate change is Catherine Hayhoe. I've got a couple of her videos on Moodle, and it's well worth your time to see her explain some of these concepts. Climate change takes the natural disasters, environmental disasters, whatever you want to call them, that we already have to deal with. It makes it that much worse. Okay. It's like, I got a 10-foot pile of crap I got to deal with, and climate change makes it 11. It makes the things we have to deal with worse, and it makes them happen more frequently. The wildfire situation in California, there's all kinds of reasons the wildfires were bad in 2020 in California. All right. Obviously, there's more people that have moved into forested areas. Forest management's a little wonky out there also, but the temperatures are higher, which means there is more evaporation from soils, which means vegetation dries out faster. So it's more susceptible to wildfire. All right. But then, and this is oftentimes lost, is that the fires will spread faster and further because of that. I mean, yes, you're going to have they're going to ignite more frequently because you got more people running around in places that there weren't people 70 years ago. But because you've got more fuel that is now susceptible to burning, these fires they burn faster, they will tear through areas faster, and they'll actually burn hotter. So faster, further, and hotter with wildfires, all else being equal. So this brings us down to the last question that I kind of got in there to address. Is it a big deal? Is it a big deal? Depends on who's asking the question. And I hate that that's that cheesy, but it is. And if you're thinking about just me, or just you, or just your aunt, or just your nephew, or just your cousin, is it a big deal to that person? Maybe not. But how does that person make his or her living? Is he or she a farmer? Is he an electrician? Does he work on an oil rig in off the coast of Louisiana? Are they building wind turbines in Texas? So when we say a big deal, we have to say, well, who's asking that question? Are we asking it as a global society? Are we asking it as a country? Because one of the things that makes sense when you start to think about it is those of us in the developed world, we've got more money than places in the undeveloped world. We can deal with these things a lot better than they can. And I mean, and this goes to the whole, inequity thing. People living in the deltas in Bangladesh really are going to have a hard time. They're poor. They've got no place to go. They can't just get in their car and drive to India. If I grew up in Virginia Beach, I grew up in Atlantic City, I grew up on the Outer Banks, I can get in my car and move to Raleigh or Richmond or DC and it's done. But we're in a very different kind of society than those folks are. Poor people, people who don't have the means that most of us do. So we're in a better position in a developed economy to deal with this. Having said that, if we don't do something, it's going to probably cost us more in the long term. By scaling back or spending some money now to scale back on how we're on our use of fossil fuels, finding other ways to generate electrons to power stuff, is a short-term loss for a longer-term gain. My big thing growing up in Virginia is I'm always thinking about sea level rise and all that infrastructure at the coastline. And it's not just beach houses. Ironically, and I think this is lost on a lot of people, a lot of these like barrier islands, whether it's the Jersey Shore, the North Carolina Outer Banks, St. Simon's Island down in Georgia, Emerald Isle, any of these places, there are inlets and little inland bays. Those are going to flood too. Unless you start pumping up sand and closing those inlets off, those other areas are going to flood too. And there's property and infrastructure. They're going to have to be dealt with there. On top of that, you have to start thinking about water tables, aquifers. As the sea levels rise, the salinity levels rise. So aquifers start to get contaminated with salt water. So there's a lot of other things that are going on other than just, well, it's a beach house, who cares? There's a lot more going on to that when we think about sea level rise. And real briefly, sea level rise is largely twofold. One, The temperature of the water is rising. And we know that when when everything warms, it expands. So that's part of sea level rise. And the other part is land ice melting and running into the ocean. You take a cube of ice, you drop it into your cup of water, it floods. I mean, it overflows. So that's what we're doing with ice sheets and ice caps. And here I'm talking about mostly Greenland and Antarctica. That's where the really main stores of freshwater land ice are. On the side, you do hear a lot about Arctic sea ice, which is important, but in terms of its contribution to overall sea level rise, it's minuscule. And when you run the equations, you can pretty much throw that out. The big issue is warming the actual ocean itself, and then melting the glacial ice from Greenland and Antarctica into the global oceans, and bringing the sea levels up. In the mean and the average, the global sea levels have come up about 8 to 9 inches in the last century, which doesn't sound like a lot, but if you look at most homes, that's the difference between water just getting your home and water starting to get into your electrical outlets. And even if it doesn't necessarily, 8 inches doesn't flood a house at the shore, when you start to get astronomical high tides, or you start to get storm surge from hurricanes and other winter storms, I don't know if any of y'all have interest here in the Northeast. There's a lot of coastal flooding for the Jersey Shore up to Boston, just because it was a regular coastal storm. It didn't have to be a hurricane, but there was almost a foot of water running along the ground of the Jersey Shore yesterday. I had friends down there who were sending pictures of it. So with a higher mean sea level, that water has a jump start to flood. So you start to see flooding, coastal flooding more frequently. That's really what it's going to be all about with sea level rise. It's not like you wake up in 1 week, I can't live here anymore. No, you start to have more and more sea level flooding, coastal flooding. It becomes often enough where your infrastructure starts to deteriorate because it gets salt water in it. You're getting salt water in your infrastructure 4, 5, 8, 15 times a year. And then property values drop and people leave. And that's how it's probably going to play out. You don't wake up in a week and, oh, everything is underwater. It's not going to work out like that. So that's a quick overview of a lot of the questions. And thanks to all of y'all for sending really good questions for the first assignment. No assignment for this week. I'm not going to worry about it. I'll have something for next week.